All right, so we've seen composition, we've seen primitive recursion. We're going to look at one more building block that the founders of computability theory felt was necessary. It's sometimes called mu recursion or simply minimization. Here's how it works. Suppose that I have a function f of two variables, x and y, which is already computable. I'm going to define a new function h of x as the smallest y such that f of x comma y is 0. It's the smallest solution to that equation, and remember, we're just looking at the whole numbers here, 0, 1, 2, 3, and so on. How might we write this in the programming languages we're used to? Well, we would use a while loop. We would start out by setting y equal to 0, and then we would say, while f of x comma y is not 0, increment y, setting it to y plus 1. Keep doing this. If you find a y such that f of x comma y equals 0, we'll fall out of the while loop. It will halt. At that point, we will return y. Well, okay, if you've done any programming, you've seen for loops and you've seen while loops, so it's kind of nice to see this show up. But what if there is no such y? What if x comma y is non-zero for all values of y? Well, then the while loop will run forever. And that's something that while loops do sometimes. They never end. And in that case, this program will never halt. But then it will never return a value, and this function will be undefined. So, as soon as you have minimization or mu recursion as one of your operators for generating new functions, or in programming terms, as soon as you have a while loop, your programs might not halt and your functions might not be defined. They might return values for some inputs but not for others. We call that kind of thing a partial function, and that, by the way, is why the word partial is in that phrase, partial recursive functions. So this already raises a lot of interesting questions. When can we tell whether a function is defined or not? Well, that's like telling whether a program will halt or not. So you might ask, do we really need these while loops? It would be nice if our programs always halted, if they always gave us an answer. And notice that for loops, as long as you don't kind of deliberately tinker with them, for loops always finish. When you enter a for loop, you're saying, for I equals 1 to 100, you know it's going to run 100 times and then it's going to be done. So an interesting question is, are there functions which are defined in every case? There's always an output that the program should give, but where for loops are not enough, do we need to include while loops in our programming language? Imagine a kind of crippled version of your favorite programming language, which has for loops and composition and so on, but it does not have while loops. Imagine if every time you began a loop, you had to state in advance how many times it's going to run before it halts for sure. Would you be able to compute all the things we want to be able to compute in that language with the missing while? In fact, the answer is no. So there's a clever function called the Ackermann function. So we've already seen how we start with the successor function, we iterate it inductively, and we get addition. You iterate addition, adding y to x times, and you get multiplication. You iterate multiplication and you get exponentiation. We don't talk about it very often, but you could iterate exponentiation and build a tower of exponents and thus create a function which grows very quickly. Well, the Ackermann function is rather cute. It takes 3 inputs, and the first input tells us what level of these inductive functions we're going to apply. Addition, multiplication, exponentiation, repeated exponentiation, and so on. By the way, this is not quite how the Ackermann function is defined originally, but I think it gets across the idea of what it's trying to do. Well, the Ackermann function for the nth level, it can be proved, needs n levels of nested for loops living inside each other. But that means that there is no program written just with for loops which computes a of n comma x comma y for any value of n, because you would have to kind of modify the program, adding more and more levels of for loops, and well, you can't do that. So the Ackermann function is interesting. It is a total function. It is defined for all values of its inputs, and yet you need while loops in order to compute it. So what this tells us is that there are functions which are recursive and defined everywhere, but not primitive recursive. We just proved that the primitive recursive functions do not cover all of the recursive functions, even including those which are defined everywhere. That's very nice, actually. If you go back to the still unsolved question of whether P and NP are different, we know it's generally hard to prove that one class of functions or problems is definitely smaller than another class, which can be computed in some more powerful way. But in this case, we really can. This also tells us that while loops are really unavoidable if you want to compute all the things that we are familiar with and normally would consider computable. But if while loops are unavoidable, this also means that sometimes our programs are not going to halt. It means we have to embrace the possibility that our programs will get stuck somehow in some kind of infinite loop and run forever. I also want to point out that the things we've seen, for and while and composition, subroutines, these show up in an entire family of programming languages, which indeed are the ones that kind of most programmers are familiar with. C, Java, most of Python, and so on. And this is no coincidence. These programming languages were invented by people who were familiar with recursive function theory, and so things like for and while loops, the ability of one function to call another as a subroutine, these grew out of this theory of what types of functions can be computed.